Hello students, I am Dr. Sangeeta Sharma, your science teacher. Today we will be continuing with chapter 10 of your science book, that is light, reflection and refraction. In our previous video, we studied about spherical lenses and the image formation by convex lenses. And in today's video, that is part 8, we will be learning about image formation by concave lenses. So let's study image formation by a concave lens. So here students, when we need to understand the image formed by a concave lens, we must recall that for image formation we need at least two rays of light, and these rays of light after refraction through the concave lens, when they will meet, there the image will be formed. हमें इमेज फॉर्मेशन के लिए कम से कम दो रेज ऑफ लाइट चाहिए जो रिफ्रैक्शन के बाद में जहां मीट करेंगी वहां हमें इमेज मिलेगी. सो यहाँ पर भी स्टूडेंट्स हम ऑब्जेक्ट की अलग अलग पोजीशंस लेंगे एंड वी विल बिगिन विथ द फर्स्ट पोजीशन ऑफ द ऑब्जेक्ट, दैट इज व्हेन द ऑब्जेक्ट इज प्लेस्ड एट infinity. So students, when the object is placed at infinity, the rays will be coming from infinity and they will be parallel to the principal axis. So the rays of light which are coming from infinity, that is where the object is placed, are going to be parallel to the principal axis. Here I have taken 1 and 2. So what we see is that the ray of light which is incident parallel to the principal axis, after refraction from the concave lens, it gets refracted in this direction. So this ray of light which is coming parallel to the principal axis, after refraction through the concave lens, moves in this direction. And similarly, the other ray of light which is again coming parallel to the principal axis, after refraction through the concave lens, moves in this direction. And now since these two rays are diverging, ये rays फैल रही हैं, that is why these rays are never going to meet behind the lens. So what we have is that we extend these refracted rays, and what we observe is that they meet at the point F1, which is the principal focus. So what we see here is that these refracted rays, on extending on the side where the object is placed, they meet at a point F1. So here the image will be formed. So we get the image at F1, which is shown by the black dot. So students, here what we observe is that the rays are not actually meeting. They are meeting on extending in front of the lens. So what we see here is that the image formed is virtual, and all images which are formed virtual are always erect. And since the size is diminished, or we can say that the size is point sized, so here the image will be virtual, erect and point sized. यहाँ पर हमने क्या देखा स्टूडेंट्स कि जो रेज ऑफ लाइट ऑब्जेक्ट इन्फिनिटी पर है, तो जो रेज ऑफ लाइट इन्फिनिटी से आ रही हैं वो पैरेलल होंगी प्रिंसिपल एक्सिस के, और रिफ्रैक्शन के बाद में लेंस के दूसरी साइड में कहीं पर भी मीट नहीं करेंगी. सो उन्हें एक्सटेंड करेंगे जब हम इन फ्रंट ऑफ द लेंस, तो वहां पर वो F1 पॉइंट के ऊपर मीट कर रही हैं, इसलिए इमेज फॉर्मेशन जो है वो F1 पर होगी. एंड द इमेज इज गोइंग टू बी वर्चुअल, इरेक्ट and point sized. So the image appears to be formed at the focus. Here we have used the word appears because they are not actually meeting, that is the refracted rays are not actually meeting, they appear to meet at the focus. So the image appears to be formed at the focus. It is virtual, erect and very small, and on the same side as the object is placed. Now let's see the second position of the object. Now here the object is placed between infinity and 2f1. Students, here we can write 2f1 or we can write c1. So what we see is, again we have to take two rays of light which are going to be incident on the lens, and then we will see how the image is formed. So the first type of ray which I have taken is the ray of light which is incident parallel to the principal axis. So this ray of light which is incident parallel to the principal axis, after refraction through the concave lens, gets refracted in this way. And the second ray of light which I have taken is the ray of light which is directed towards the optical center. And as we know, students, that the ray of light which moves through the optical center or which passes through the optical center passes through the lens undeviated, that is, it moves in a straight line, it does not change its path. So this ray of light will move straight after refraction through the concave lens. Now again what we see is that these two rays of light after refraction, that is the refracted rays of light, are never going to meet on the other side of the lens, but on extending. But on extending in front of the lens, what we see is that they are going to intersect or they are going to meet at this point, and here the image will be formed, that is A dash B dash. So students, यहाँ पर हमने क्या सीखा कि अगर ऑब्जेक्ट की पोजीशन बियॉन्ड 2f1 या बियॉन्ड c1 हो, दैट इज इंफिनिटी और 2f1 के बीच में हो, तो जो इमेज फॉर्म्ड है वो लेंस के सामने की ओर ही फॉर्म हो रही है। दो रेज ऑफ लाइट हमने ली जो रिफ्रैक्शन के बाद में लेंस के पीछे नहीं मीट कर रही है, लेंस के आगे की तरफ ही वर्चुअली मीट कर रही है, तो हमें इमेज मिलती है A dash B dash पर। So students, what we see here is that the image formed is diminished and it is erect, and since the rays of light, that is the refracted rays of light, are not meeting actually, they are meeting only on extending in front of the lens, so we have a virtual image, and here the image is erect. What we can see here is that the object was upright having its head here, and the image is again upright having its head here. So the image formed is virtual, erect, and as we can see that the image is smaller than the object. So the size has been reduced, it is a diminished image. So when the object is beyond 2f, the image appears to be formed between F and O. Now what we see here is that the image is formed between the optical center and the principal focus, and the image is virtual as the refracted rays are not meeting actually. It is erect because the object and the image both are upright, and it is smaller than the object and on the same side as the object. So what we see here is that when the object is placed between infinity and 2f1, the image is formed between the principal focus and the optical center of the lens. Now we will take one more position, that is when the object is at 2f. Now students, when the object is placed at 2f1, which can be said as C1, then what we see is, again we will see the image formation, and we will take two rays of light. The first ray of light which is incident parallel to the principal axis after refraction through the lens moves in this direction, and the ray of light which is incident towards the optical center goes undeviated after refraction, that is it moves in a straight line. Again these two rays of light are never going to meet behind the lens, or you can say on the other side of the lens. On extending, what we see is they are again going to meet at this point, and here we will have a image formed. Now students, again the image is formed between F1 and O. Since the refracted rays are not meeting actually, they are meeting only when extended in front of the lens, so the image is virtual. Again what we see here is that the object and the image both are upright, that is the image is erect, and again here the image is smaller, that is the size of the image is smaller as compared to the object. So this is seen, this is observed that whatever be the position of the object, ऑब्जेक्ट की किसी भी पोजीशन के लिए इंफिनिटी और ऑप्टिकल सेंटर के बीच में, ऑब्जेक्ट की पोजीशन अगर इंफिनिटी और ऑप्टिकल सेंटर के बीच में कहीं पर भी रखी हो तो इमेज हमेशा F1 और O के बीच में ही बनेगी. So students, we will have only two positions of the object. First, when the object is placed at infinity, the image formed will be at the focus in front of the lens. And when the object is placed anywhere between infinity and the optical center of the lens, anywhere between infinity and the optical center of the lens, what we see is that the image will be formed always between the principal focus and the optical center, and the image will always be virtual, erect and smaller in size. Students, यहाँ पर हमने क्या सीखा कि ऑब्जेक्ट की पोजीशन अगर इन्फिनिटी और ऑप्टिकल सेंटर के बीच में कहीं पर भी हो तो इमेज हमेशा F और O के बीच में ही बनती है। इमेज हमेशा प्रिंसिपल फोकस और ऑप्टिकल सेंटर के बीच में ही बनती है। कोई भी पोजीशन ले लीजिए, चाहे वो आप 2f1 के बियॉन्ड ले लीजिए, 2f1 पे ले लीजिए, 2f1 और f1 के बीच में ले लीजिए, f1 पर ले लीजिए, कहीं पर भी ऑब्जेक्ट आप प्लेस कर लीजिए, इन्फिनिटी और ऑप्टिकल सेंटर के बीच में हमेशा जो इमेज फॉर्म्ड होगी वो होगी F1 और O के बीच में, या यूं कह सकते हैं ऑप्टिकल सेंटर और फोकस के बीच में। एंड द इमेज इज ऑलवेज गोइंग टू बी वर्चुअल, इरेक्ट एंड स्मॉलर इन साइज। सो लेट्स समराइज दीज टू पोजीशंस ऑफ image formation in a concave lens. So the image formation by a concave lens is summarized here in this table. And what we see is when the position of the object was at infinity, the position of the image was at focus f1, it was highly diminished, or what we can say is it was point sized, the image was virtual and erect. Then the second position, which can be any position between infinity and the optical center of the lens. Whatever be the position of the object, what we find is that the position of the image is always between f1 and the optical center O, and always the image is smaller, that is the size of the image is diminished as compared to the size of the object. And here also the nature of the image is going to be virtual and erect always. So what we see here is, students, that in case of concave lenses, image is always virtual and erect. But in case of convex lenses, what we saw was for the first 5 positions of the object, we had real and inverted image, and for the 6th position of the object, when the object was placed between F and O, we had a virtual and erect image. So keeping this in mind, let's move further and let's learn about the sign convention used for the lenses. Now students, the sign convention used for lenses is same as that used in case of mirrors, but again we will recall and revise all the sign conventions used. So the sign convention for lenses is same as that for mirrors. Now let's revise one by one. The first sign convention says that the object is always taken on the left side of the lens. This now you have learnt by heart, that the object is always taken in front of the lens. Mirrors के केस में भी हम ऑब्जेक्ट को हमेशा कहाँ लेते थे? लेफ्ट हैंड साइड पे। और यहाँ पर लेंस के केस में भी, चाहे वो कॉन्केव लेंस हो चाहे वो कॉन्वेक्स लेंस हो, हमेशा हम ऑब्जेक्ट की पोजीशन क्या लेंगे? ऑब्जेक्ट की पोजीशन लेंगे लेफ्ट हैंड साइड पे, या यूं कह सकते हैं कि लेंस के फ्रंट में। नाउ the second sign convention says that all the distances are measured from the optical center of the lens. Mirrors के केस में वहां पर पोल होता था, हम पोल से सारी डिस्टेंसेस मेजर करते थे। लेंस के केस में क्या होता है? पोल नहीं होता, यहाँ पर हमारे पास में लेंस का जो सेंटर है, जो कि प्रिंसिपल एक्सिस के ऊपर लाई करता है, ऑप्टिकल सेंटर, उस सेंटर से हम सारी डिस्टेंसेस को मेजर करेंगे। वी विल मेजर all the distances from the optical center of the lens, both type of lenses, concave and convex. Then the third sign convention says that the distances traversed in the direction of light are taken as positive, and those in the opposite direction are taken as negative. All the distances in the direction of incident ray of light is taken as पॉजिटिव, और इंसिडेंट रे ऑफ लाइट को हमेशा हम किस डायरेक्शन में लेते हैं, लेफ्ट टू राइट, दैट इज टुवर्ड्स द पॉजिटिव एक्स एक्सिस. सो जितनी भी डिस्टेंसेस हमें ऑप्टिकल सेंटर से मेजर करते हुए इंसिडेंट रे ऑफ लाइट की डायरेक्शन में लेनी पड़ेंगी, उन सारी डिस्टेंसेस को हम पॉजिटिव लेंगे. और जो डिस्टेंसेस ऑप्टिकल सेंटर से मेजर करते हुए इंसिडेंट रे ऑफ लाइट की अपोजिट डायरेक्शन में लेनी पड़ेंगी, उन सारी डिस्टेंसेस को हम नेगेटिव लेंगे. ऑल द डिस्टेंसेस in the direction of incident ray of light, which is always taken from left to right. So all the distances measured in this direction will be taken as positive, and all the directions opposite to this direction will be taken as negative. Now the fourth sign convention is that all the distances above the principal axis are considered to be positive and below the principal axis are considered to be negative. Now students, जो भी distances principal axis के ऊपर की ओर measure की जाएंगी, जैसे कि हमारा object रखा हुआ होता है तो हमें distance कहाँ measure करनी होती है, principal axis के ऊपर, तो वो सारी distances हमेशा हम क्या लेंगे, positive. और जो डिस्टेंसेस हमें प्रिंसिपल एक्सिस के नीचे की ओर मेजर करनी होगी, जब हमारी इन्वर्टेड इमेजेस होती हैं, तो उस केस के अंदर क्या होगा, वो डिस्टेंसेस हमें क्या लेनी होंगी, नेगेटिव. नाउ लेट्स समराइज ऑल दीज 4 साइन कन्वेंशंस फॉर लेंसेज थ्रू अ फिगर. नाउ हियर आई हैव शोन अ convex lens. This is applicable for both convex and concave lenses. So here students, the direction of incident light is taken from left to right, and all the directions measured in this direction are going to be taken to be positive. So in the direction of incident light we will have positive distance, and against the direction of incident light, will be taken as negative distances. Here the object is placed on the left side of the lens, and all the height which are measured upwards will be taken as positive, and all the heights which are measured downwards will be taken as negative. So these are the sign conventions which we are going to use for solving numerical problems related to spherical lenses. Now students, here we must understand one more thing, that the focal length of a convex lens is positive, whereas the focal length of a concave lens is negative. Now why we have taken this? Let's understand. So for convex lens, what we see is, say this is a convex lens, say this is the principal axis and the object is placed over here. Then the ray of light which are coming parallel to the principal axis, after refraction will always go through the focus, and since the focus is on the other side of the lens, since here the focus is, this is the focus, and since the focus is on the right hand side, that is, say this is the optical center, so we have to measure the distance of the focus from the optical center. So we have to move in a direction of the incident ray of light. So the focus is on the right hand side, and hence the focal length is always going to be taken as positive. कॉन्वेक्स लेंस के केस में क्या है स्टूडेंट्स, कि जो रेज ऑफ लाइट पैरेलल इंसिडेंट हो रही हैं कॉन्वेक्स लेंस पे, वो रिफ्रैक्शन के बाद में फोकस पर मीट कर रही हैं, और फोकस राइट हैंड साइड पर है लेंस के, दैट इज इट इज ऑन द other side of the lens, and in order to measure the distance of the focus from the optical center, we have to move in the direction of the incident ray of light. That is why the focus is taken to be positive in case of convex lenses. Now let's understand this for concave lenses. Let this be the concave lens, let this is the principal axis. Now what we see is, suppose the object is placed over here, then the ray of lights which are incident parallel to the principal axis after refraction, what we see is that the ray of lights are going to meet. They appear to meet at F. That is what we see here is that the rays of light after refraction are diverging. That is, they are never going to meet on the right hand side of the lens, but on extending they appear to come from the focus. And since the focus is on the left hand side, the focus is on the left hand side of the concave mirror. So, in order to measure the distance, we have to move in a direction opposite to the direction of incident ray of light. So, here F is going to be negative, where F is the distance between the optical center and the principal focus. So, F is going to be negative. This is what we have written here, that the focal length of convex lens is positive, whereas the focal length of concave lens is always negative. Now, let us learn about the lens formula. Students, we have learnt about the mirror formula in case of mirrors. There what we saw was that there was a relation between the focal length, the object distance and the image distance, and again here we will have a relation between the focal length, the object distance and the image distance, but here the relation is a bit different. Kindly take care. So, here what we have is that the lens formula gives the relationship between the object distance u, the image distance v and the focal length f, and the relation is 1 upon v minus 1 upon u is equal to 1 upon f. Now, students, here we have a negative sign, there we had a positive sign and here we have a negative sign. So, keep in mind, for the case of mirrors, that is spherical mirrors, we always had the mirror formula which was 1 upon f is equal to 1 upon u plus 1 upon v. Here in case of spherical lenses, we have lens formula and here the relationship is 1 upon f is equal to 1 upon v minus 1 upon u. So, this is the lens formula, and before substituting the values, we must take the values with proper signs using the sign convention which we have learnt. Now, let us understand what linear magnification is. Again students, the linear magnification means that there is some relation between the image size and the object size, and M gives us an idea whether the image is bigger, that is magnified, or the image size is smaller, that is demagnified. So, by the value of M, again we will get an idea about the size of the image and the size of the object. So, the linear magnification produced by a lens is defined as the ratio of the size of the image as formed by refraction through the lens to the size of the object. So, linear magnification, which is represented by small m, is the ratio of size of the image and size of the object. If size of the image is represented by capital I and size of the object is represented by capital O, then it can be taken as I upon O, and as we were already using H2 upon H1, that is H2 for the height of the image and H1 for height of the object, here again we will use H2 upon H1. So, this is the formula for linear magnification, which is ratio of size of image and size of object. Now, it can be expressed in one more way. So, the magnification produced by a lens is also related to the object distance and the image distance v. The object distance is u and the image distance is given by v. So, m, which was equal to H2 upon H1, is also equal to the ratio of the image distance and the object distance from the lens. So, students, lens formula और मिरर फार्मूला दोनों में कंफ्यूज नहीं होना है. मिरर फार्मूला में पॉजिटिव साइन आता है और लेंस फार्मूला में नेगेटिव साइन आता है. बट मैग्निफिकेशन के केस में जब हम मैग्निफिकेशन पढ़ रहे थे स्फेरिकल मिरर्स के लिए, तो वहां पर -v/u आ रहा था मैग्निफिकेशन के लिए, और लेंसेज के लिए मैग्निफिकेशन v/u आ रहा है. सो टेक केयर. नाउ द लीनियर मैग्निफिकेशन इज positive when the image formed is virtual, and the linear magnification is negative when the image formed is real. This is same as the case of spherical mirrors. Now students, again we must revise, or we can say we must recall the values for m, which gives us an idea about the nature of the image. Now if m is positive, we are going to have a virtual image, and all virtual images are always erect. And if the value of m is negative, then we are going to have a real image, and a real image is always inverted. And one more thing students, that the value of m, if it is equal to 1, then the size of the object and the size of the image which is formed after refraction through the lens is going to be the same, or what we can say is that the distance of the object from the lens and the distance of the image from the lens is going to be the same. But if the value of m is less than 1, then what we say is that the size of the image is less than the size of the object, that is demagnification has taken place. Image is smaller as compared to the size of the object, and if the value of m is greater than 1, then what we say is that magnification has taken place and the size of the image is greater than the size of the object, or we can say that the distance of the image formed from the lens, and we can say that the distance of the image formed from the lens is greater than the distance of the object from the lens. So this was linear magnification. Now let's learn about the power of a lens. Now students, basically what power means? Now power is the ability of the lens to converge और diverge the rays of light falling on it. जितना अच्छे से converge करेगा, इकट्ठा करेगा लाइट को, हम कहेंगे वो लेंस जो है वो बहुत पावरफुल है, या वो जितना अच्छे से डाइवर्ज करेगा रेज ऑफ लाइट को, उतना ही अच्छा वो लेंस कहलाएगा पावर की टर्म्स में. सो हियर व्हाट वी सी इज दैट पावर ऑफ लेंस इज डिफाइंड एज द एबिलिटी ऑफ द लेंस टू कन्वर्ज in case of convex lenses and diverge in case of concave lenses, the rays of light falling on it. That is, the power of a lens is the ability of the lens to converge or diverge the rays of light falling on it. जितना अच्छे से converge या diverge करेगा, उतनी ही ज़्यादा उसकी power मानी जाएगी. As a convex lens converges the rays of light falling on it, power of a convex lens is said to be positive. Convex lenses की power को हमेशा positive लिया जाता है, and as a concave lens diverges the rays of light falling on it, power of a concave lens is said to be negative. So students, let's understand mathematically what power of a lens is. This is basically a theoretical definition, and in order to solve the numerical problems, we must have a mathematical definition for power of a lens. So the mathematical definition for power of a lens is that power of a lens is given by reciprocal of focal length of the lens. That is, power of the lens, which is denoted by capital P, is equal to 1 upon f, where f is taken in meters. So the power is reciprocal of the focal length of the lens. Now the SI unit of power of lens is diopter, and it is denoted by letter capital D. Now here students, we have taken the focal length in meter. So if the focal length is taken in meter, then diopter, you must understand from here that it is going to have the units of 1 upon meter, that is meter inverse, and this meter inverse is diopter. So when F is equal to 1 meter, the power is equal to 1 upon 1 meter, and that is equal to 1 diopter. So what we see is that basically diopter is meter inverse. Thus 1 diopter is the power of a lens of focal length 1 meter. This is the definition of diopter, students, that 1 diopter is the power of a lens of focal length 1 meter. Now let's see that when we have a combination of lenses, then power of lens is going to behave in what manner? So what we see is that power of combination of lenses. When a number of thin lenses are placed in contact with one another, the power of the combination is equal to algebraic sum of the powers of individual lenses. Now suppose, students, we have a number of lenses kept side by side. That is, we can have one lens, the second lens, the third lens, and so on. Let the power of the first lens be P1, power of the second lens be P2, and power of the third lens be P3. Then the power of all these three lenses when taken together will be given by simply the algebraic sum of the powers of the individual lenses. That is, we have to add them simply. Now since power is reciprocal of the focal length, so the definition can go like this also, that 1 upon F is equal to 1 upon F1 plus 1 upon F2 plus 1 upon F3 plus so on, as the case may be. So students, what we learned today is that we learned how image is formed in case of concave lenses, and we saw that basically there are only two positions of the object. First, when the object is placed at infinity, and second, when the object is placed anywhere between infinity and optical center of the lens. Then we learnt about the sign convention for lenses, and then we learnt that how lens formula is used in case of spherical lenses and how it is different from the formula, that is the mirror formula. Then we studied about the linear magnification and then the power of a lens, and we learnt about the power of combination of lenses. Now students, this is what we learnt about refraction of light, that is the image formation by spherical lenses. Now we are ready to solve the numerical problem. So in our next video we will study and we will solve all the numerical problems given inside the text, inside the chapter and behind the chapter. So till then, stay safe, stay healthy, bye.